In other words, as x, what's happening to the function as x approaches a particular value? And so the first thing we want to look at is think about this function f of x equals 3 over x minus 2. Hopefully we have an idea of what that function looks like. Are there any discontinuities? Yes. Where would that discontinuity occur? X equals 2. Is it going to be removable or non-removable? Non-removable. Okay, so it looks like we probably are going to have a non-removable discontinuity when x equals 2. So just as an idea, yes ma'am?
Why is it non-removable?
Why is it non-removable? Noah, what's your comment on that? There were several.
Because it's an asymptote.
Okay, you think it's an asymptote? How do you know it's an asymptote?
Because it's something over x.
Okay.
Okay, that makes sense.
Let's think about what might happen. If we take the limit as x approaches 2 from the left, what do you think is going to happen there? Now notice, we know kind of what this looks like because it's a transformation of that reciprocal function. And so this 3 on top is just going to stretch things a little bit. The reciprocal function looks a little bit like this. Okay, I'm just sketching it. I know it's not going to be exact, the stretch and everything, but that function is going to look something like that. So, as x approaches 2 from the left, what's happening to the value of the function? Okay, it's going to, does the limit exist? No, but we can describe what's happening, and it looks like that it's going to negative infinity. That doesn't mean that the limit does exist. It just tells us what's happening here. What about if we take the limit as x approaches 2 from the right? It's going to positive infinity. We can see that by looking at the graph. Now, you may not always have a graph handy to look at. Obviously, there are several tests here, and a large part of the AP test is non-calculator. So, having an idea of what some of these functions look like is helpful, but I'm also going to show you some things you can do to figure out, okay, is it going to positive infinity? Is it going to negative infinity? What's happening here? And we'll be able to do that. But notice, yes?
Do we need to write it does not exist and then negative infinity, or does it?
For my purposes, I would prefer you do that.
Okay.
That way I know you understand there's no limit, but you understand what's happening to the function. Okay, if a limit increases or decreases without bound, doesn't mean that there's not a limit. That there's a limit. It just means the limit still doesn't exist. But this can tell us how it fails to exist. What's going on here? What I want us to do is look at page 81. There's an exploration there. All right, we're going to look at a definition. If f of x approaches infinity, either negative or positive. Okay, if f of x approaches infinity, whether it's negative or positive, as x approaches c, from the right or the left, then x equals c. Well, I'll go ahead and put from the right or the left. Then x equals c is a vertical asymptote of f of x. Now, that's not the definition we saw for vertical asymptotes last year. We didn't look at what was happening to the function. We just saw, okay, it's undefined here. Nothing cancels out, so we have a vertical asymptote. But here, we're defining this vertical asymptote is if the function approaches either positive or negative infinity at c, then x equals c is a vertical asymptote. So now f and g are both continuous on an open interval. This is a theorem, I think in your book it's theorem 1.14. Like I would expect you to remember that. But f and g are continuous on an open interval. That contains c. F of c, if f of c is not equal to 0, and g of c equals 0, then the graph of the function that's defined as h of x equals f of x over g of x has a vertical asymptote at x equals c. So, this is just another theorem about vertical asymptotes. This requires a value for the numerator at x equals c. It requires that f of x has some number value, that it's not 0 over 0. Because if you get 0 over 0, what do you have? Indeterminate. And if it's indeterminate, we have to do a little bit more looking into it. So, you get a number on top and 0 on bottom, then you have a vertical asymptote at that x equals c value. And that's pretty close to how we defined vertical asymptotes last year. So let's look at some functions and see if we can determine what the vertical asymptote is. Okay, what's my vertical asymptote, Noah? Or is there one? Just negative 1? X equals negative 1. All right. Okay, Adam, what about here? G of x is x squared plus 1 over x squared minus 1. Do I have any vertical asymptotes? Yeah, and I don't care if you do it that way, that's fine. X equals plus or minus 1. Let's think about this trig function. F of x equals the cotangent of x. So it's the same as 1 over tangent of x, or if you don't remember where those asymptotes are, what could you do?
Plug in values.
You could plug in values. You could think about, what is the cotangent? What's another definition of the cotangent?
It's the inverse of the tangent.
It's the inverse of the tangent, but that doesn't do us a whole lot of good. Okay, because the one we're most familiar with are sine and cosine, probably. So if we think about this as cosine x over sine x, where's the sine x equal to 0? At 0, pi, 2 pi, 3 pi. So here we have vertical asymptotes when x equals n times pi, where n is an integer. Why do we have to specify that n is an integer?
Because it has to be a whole circle, right?
Because it has to be a whole number.
Not a whole, it doesn't have to be a whole number.
Because it has to be a full circle.
Maybe that's
A real number.
I don't know.
A full
A whole number is like 0, 1, 2, 3, 4, 5.
Yeah.
So it has to be.
So a whole number including.
But it can be
negatives.
negative.
So it's an integer.
Exactly. So that's
No fraction, that no,
No
no,
fraction.
there's no fractional values of pi that would give us
Correct.
an asymptote, which is why we have to specify. Angela, you need to stand up. That's why we have to specify. Asymptotes here.
Negative 2 and negative 2.
X equals 2 and x equals negative 2. That's where we have vertical asymptotes.
Nope, so you can factor it.
You can factor it.
You can factor it.
Okay, we always need to check. Do we have any common factors? So, how does the numerator factor? X plus 2. Is that right? Is it going to be x plus 2?
X minus 2. X minus 2 and x plus 4.
X minus 2 and x plus 4 over. So what happens when x is 2?
There's one.
Yeah.
Okay, we have a removable discontinuity when x is 2. What happens when x is negative 2? Vertical asymptote when x is negative 2. So you can't just look at the denominator. You also have to look at the numerator to make sure that you don't have a removable discontinuity. Function, I want to find the limit as x approaches 1 from the left of f of x. And then I want to find the limit as x approaches 1 from the right of f of x. Now, is this going to be an asymptote when x equals 1?
Yes.
Okay. Yes. Because how does that factor? Just
X
new.
times X minus 3.
Okay, so here we would have x times x minus 3 over x minus 1. All right, so I want to try to determine if, from the left, am I going to positive infinity or negative infinity? Now, without just graphing the whole thing, we can choose a couple of points on either side and see, are we increasing or decreasing? So if we're looking from the left, we know that here, if I were just kind of sketching, I'm not trying to do a full graph, but at x equals 1, we'd have an asymptote. So what we can do is figure out, okay, coming at it from the left, are we increasing? Is the function going up or is it going down? Because it's an asymptote, we know it's either going to positive or negative infinity. So if x is 0, is this function that I have defined going to be positive or negative? It's going to be 0.
So neutral.
Yeah.
All right, so I either need to back it further away or get closer to the asymptote. So if we choose x is negative 1, I only need to know is it negative or positive. I really don't care what the value is. Is it negative or positive? So if I choose negative 1, I'm going to have a negative times a negative over a negative, right? Yes. So is that going to be negative or positive?
Negative.
That's going to be some negative value. So does it look like this function is increasing or decreasing? It's increasing, so this is going to go to positive infinity. Now let's think about it the other way. As I approach 1 from the right, all right, let's just use something easy. You could use fractions if you want to, but let's just use something easy. Let's use 2. If I use 2, I'm going to have a positive times a negative over a, so is that going to be negative or positive? Negative. So it's going to be down here somewhere. And then if I choose 3, we're going to have 0. So what does it look like is happening there?
Decreasing.
It's decreasing, so this one's going to negative infinity. Okay, properties of limits. Okay? C and L are real numbers. And F and G are functions such that the limit as x approaches C of f of x is equal to infinity, and the limit as x approaches C of g of x is some real number L. Okay, one function has a limit of infinity, and one function has a limit that's a real number. Right, Adam? Okay, couldn't tell if your eyes were open or not. All right, so if we take the sum or difference then the limit as x approaches C of f of x plus or minus g of x. This is going to be infinity plus or minus L. What do you think that's going to be? Infinity. Because infinity minus or plus or minus a number is still infinity. So if one of your limits is infinity, and you're adding or subtracting another function that has a real number limit, the limit of the sum is still infinity. If we take the product of the limit as x approaches C of f of x times g of x. Well, if we have infinity times a number, what do you think that limit's going to be? Infinity. Okay, it's infinity if L is greater than 0 and negative infinity if L is less than 0. And then finally the quotient if we take the limit as x approaches C of g of x over f of x. Remember, this is going to be some real number L over infinity, and here the limit's 0. So anytime you get a number over infinity when you take the limit is 0. It would still be 0. Wouldn't matter.
Because for the sum or difference, would that matter? Would it be negative infinity?
Oh, yes, it would. It would. Okay.